These are the references shown here for the actinide chemistry course, including the general actinide chemistry, actinides in the environment, as well as the transactinides. So we have discussed about the actinide complexation and separation. Now today we'll be discussing about actinides in the environment. In some of the previous lectures, we have discussed about the factors which are responsible for this actinides in the environment. Today we will be discussing about the factors in more detail about the actinides in the environment. Now there are several actinides we know in the Earth's crust. Already we have discussed before, like uranium, thorium, to some extent even actinium and protactinium. But neptunium and plutonium are also found in nature at very, very minute concentrations. But we know that they are the activation products in the nuclear reactor. So then how this neptunium and plutonium, we can say that they may be possible in the nature? That is because of the natural reactor in Oklo that I have already mentioned in one of the previous lectures. That certain observations that support the occurrence of the natural reactor at Oklo in Gabon, West Africa, is because of the low uranium-235 content. Because we know that this natural uranium should have around 0.72% of uranium-235, but in the Gabon area, this natural reactor, whatever we call, there the uranium-235 content was found to be lower than this 0.72%, which is present in the ores. Then there is also this large concentration variation for this uranium-235, which is less than 0.5% it is seen, and also this high content of neodymium-143 and low concentration of 142 neodymium. That is a signature of some nuclear reaction was taking place at that place. Other factors which are responsible for the radionuclides in the environment, the sources are the nuclear test. So due to the nuclear test, nearly 4.5 tons of plutonium are released into the environment, and this various activities in the nuclear fuel cycle that also can have, like reprocessing, waste management, that can also contribute to the presence of plutonium and other heavier actinides in the environment, like neptunium. There can also be accidental release. Some of the accidents I have mentioned here in this table below, like the Windscale accident in 1957 in UK, and there are some of these categories of these accidents which are mentioned in the footnote of this table. That is, number 5 category is the accidents with wider consequences. Number 6 is serious accident, and number 7 is major accident. So this in the former Soviet Union also there was an accident in 1957, that is the KISS team, and it is falling in the category 6. That's a serious accident. 3 Mile Island in USA 1979 falls in category 5. And this Chernobyl reactor accident, which is now in Ukraine, it is 1986. The accident took place and it is falling under the category 7, and also 2011, the Fukushima Daiichi nuclear reactor accident, that is in Japan, and it falls in the category number 7. Now there was an interesting observation very close to the Nevada test site, where the large number of nuclear weapon testing has been done. Around 828 nuclear tests have been conducted at the Nevada test site between 1956 to 1992. The left hand side figure gives details of the test sites. where the tests have been taken place, like this Benham test site, Molbo test site, Typo test site, Belmont test site. So there are different testing sites where the nuclear weapon testing has been carried out. And there were some wells which are away from this nuclear test site. So that is something called the ER25 set of wells. So this well complex which is there at the slightly away from this nuclear test sites like Benham, Tybo, Belmont and Molbo. So in this well actually this drilling has been done and the samples of plutonium has been detected, and they found that this signature of this plutonium, that is the 240 to 239 isotopic ratio, is corresponds to that of the Benham test site. So which is much away from this well ER25, that well complex number 1 and number 3 well, they were having these plutonium activities which matched with the 240 to 239 ratio of the surface and the cavity glass activity at the nuclear test site, at the Nevada test site of the Benham test site. And this shows here for the Benham how this testing has been done, and this has been modeled that probably there is some groundwater transport of this plutonium which is going here, and very close to the well, actually this is the well complex where these samples have been taken, well number 1 and well number 3, and the sample are taken few meters deep from the earth surface at the well number 1, and at well number 3 at a deeper place the sampling has been done. And both places they have found that even though the Tybo test site is very close to the place where drilling was done, but the signature was that of the Benham nuclear test site, that suggests that the plutonium from Benham test site has migrated to the well of the well number 1 as well as well number 3. This is due to the typical mechanism of plutonium migration, which will be discussed in the next lecture. Now, what are the factors actually which is deciding these actinides in the environment? First thing is of course the oxidation state, which is also considered as the EH value, the hydrolysis, which depends on the oxidation state as well as the pH value. You know that this groundwater pH can be different places. Same also with the seawater. Seawater has a different pH. Now other factors which are also relevant is the complex formation. We know that if it is hydrolyzing, then the complex formed is the hydroxo complex. But apart from that, if there is any other complexing agent which is present in the groundwater system or in the environment, and also their concentration, the concentration is large, then the fraction of plutonium or the actinide which is present in the complex form will be relatively larger. And also if the complexation constant is higher, then also the plutonium or the actinide in the complex species will be large. Next, of course, is the solubility. Now, what is the solubility of this complex which is formed? Whether this complex is soluble in the groundwater system or this complex is precipitating. This also matters. If it is soluble complex form, then it can go in the flow of this groundwater, and migration can be a relatively longer distance. And also there can be another thing which is called the complex formation and also colloid formation. There can be colloid formation of this plutonium or other actinides which are present in the environment, and this colloid formation, this depends on the pH hydrolysis constant as well as the amount of the actinide present. And there can be also these colloids which are formed, they can act as carriers and they can also serve other actinides. So this is called as colloids, which I will be discussing subsequently. And then another factor is the sorption. This depends on the actinide species which is present in the groundwater system. Also it depends on the ionic species and what are the complexing ions present, and also the colloids which are present in the groundwater system. So finally there is a filtration effect. It depends on the size and particulate matter which is carrying the actinides, and in the rock surface it can get filtered So that is how the actinides in the particulate matter, it can be immobilized on the rock surface. And all these factors are part of the speciation of the actinides, which is depending on the environmental conditions. Now, what is the speciation? The speciation may be defined by the determination of various chemical and physical forms of the element, in this case the actinides, under investigation, such as its oxidation state, all possible inorganic or organic complexation, and also the precipitation, etc. There are methods in which the speciation can be understood, and also you can find out the nature as well as the amount of the species which are formed involving the actinides, and the techniques are same: EXAFS, JANES, TRLFS, and also XPS. So these are the techniques which are used. These techniques, they get actually a better understanding of the surface as well as aqueous speciation of the actinides. Now, why study this speciation? As we know, the presence of actinides is dangerous if it goes to our food chain, because its radiotoxicity is high. Also, the actinides and the heavier elements, they have very high chemical toxicity. And both these factors, this radiotoxicity as well as the chemical toxicity, are going to be harmful for the living beings. And also these chemical properties of these actinides and their complexes, which decide the migration of actinides. So what are important factors here is, first, of course, is the complexation, which also includes the hydrolysis of the actinides. Then whatever these complexes are formed, whether they are soluble in the groundwater system or not. Then their mobility. Now the mobility can be as such also, but if it is not forming a colloid, then naturally the mobility is going to be much less. So that is why the colloid formation is going to be important factor in this migration of the actinides. We will be discussing about these colloids in detail subsequently in this lecture. Finally, the bioavailability. Now this, whatever radionuclides are, for example plutonium, if it is migrating in the groundwater system, it is also available in the aquatic system, like the fish and other marine living species which are there. Then it enters the food chain, and that is how this becomes toxic to the human being. So basically we have to evaluate all these factors: solubility, mobility, and bioavailability. But in this lecture, we'll be mostly talking about solubility and mobility. This bioavailability and toxicity we are not going to cover in this lecture. Now the factors which are deciding speciation are pH, which is existing in the nature, that is the particularly the groundwater system, the marine conditions. Then oxidizing reducing conditions, termed as the EH, and also the presence of inorganic and organic complexing agents. So these are the main factors, that is the pH, EH, and the complexing agents, which decide the speciation of the actinides. In this particular case, we have taken example of neptunium-5. Neptunium-5, as you know, it is existing as the NpO2 plus as the ionic species, and this is considered to be most mobile of the other neptunium species, ionic species, like neptunium-4 plus, neptunium-3 plus, or neptunium O2 2 plus. This is the neptunium hexavalent neptunium ion. So compared to all these species, the neptunium-5 species is more mobile, and that is why we are considering here the neptunium-5 speciation. We give the distribution of the neptunium-5 species as a function of the pH, and the concentration of neptunium taken here is 10 to the power minus 7 molar. You can see here that at low pH values, you get this neptunium-5 species, which is the black line which is showing here, up to pH around 9 or so. You can find this neptunium-5, that is NpO2 plus species, is predominant. Beyond that, it is going to undergo hydrolysis, and there is a possibility of formation of NPO2OH, which is a neutral species, or NPO2OH twice minus, that is an anionic species. So you find that first this NPO2OH species which is forming, and then subsequently it is forming the NPO2OH2 minus species. So that is how at pH greater than 12 you get the anionic species of neptunium. Now this EH-pH diagram is also called as the Pourbaix diagram, which is already discussed in one of the previous lectures. And this shows actually the stability of the particular species under a given pH and also atmospheric conditions. So this diagram indicates actually which species they predominate under any given environmental condition of PE and pH. So this side figure is showing for the neptunium again, and you can see here this is the area in this Pourbaix diagram. This marks the region where a single species is stable, very clearly shown here. This is the area which is demarcated in this, and this is where the NPO2 plus species is stable, and that is how for the subsequently also for the other areas also this is marked how these species are stable in which area. Also these lines indicate two species are coexisting together. These vertical lines, so they mentioned, is a purely acid-base reaction, and this doesn't depend on the EH value. And the horizontal lines on the other hand, they show that these are pH independent reactions, and also they are not dependent on the EH values, the potential, whatever is prevailing under the condition. Now the slope of the lines suggests that both the acid-base as well as the redox-dependent reactions are considered in this case, or both are prevailing. Now we also see this effect of pH, EH and complexing agents on the speciation of the actinides. Now what are the complexing agents? Mostly under the groundwater condition we have this humic acid and the fulvic acid. So the humic acid actually it is the plant origin acid, which is after many years it is transformed into the humic substances. Now these humic substances, they have a very complex structure and it varies with the source, age and temperature as well as other conditions. This composed of different fractions, that the humin fraction is insoluble under all pH conditions, and the humic acid is insoluble at a pH value less than 2, and the fulvic acids are soluble under all pH conditions. So mostly because of the humic acids are very complex structure, so the studies with the actinides are with the model compounds which mimic part of the humic substances. Here I have shown a schematic of this, how this humus is first you can extract with the alkali, and which is insoluble, that is termed as the humin, and which is soluble, that if it is treated with acid and precipitated, that is termed as the humic acid fraction, and which is not precipitated, that is the fulvic acid. And then you can redissolve the humic acid, and you can again add electrolyte and you get precipitation. It is something called a gray humic acid, and which is not precipitated, it is called the brown humic acid. This is the representative structure of the humic acid is given here. Now this humic complexation is effected by controlling the pH. You know that by increasing the pH, there is increase in the strength of this humic acid complexation. That is because some of the functional groups, like it has the carboxylic acid as well as the phenolic type of groups are there, which gets deionized and you get CO minus or O minus type of functional groups which are taking part in the complexation with the metal ion, or in this case the actinide ions, and that is only possible if we increase the pH to very high values. So basically humic acids will have a number of pK values. If it is whether it is a carboxylic acid functional group or a phenolic functional group, the phenolic group will be at a higher pH value, it will be dissociating, and there is no single structure which is able to satisfy all properties of the humic acid, and its properties may change with the place of origin of the humic acid. Now while considering the stability of these humic acid complexes, as already mentioned before, the tetravalent actinides will be forming much stronger complexes than the trivalent, than the hexavalent. And in the set of tetravalent actinide ions, you find that which is having higher ionic potential, that forms a stronger complex. So plutonium 4 forms a stronger complex with the humic acid compared to uranium 4, which in turn forms a stronger complex than thorium 4. And thorium 4 forms stronger complex than americium 3 or other trivalent actinide ions, which in turn forms stronger complex than the uranium 6 ion, that is the uranyl ion. And this actinide humic acid complexation, this can modify the radionuclide oxidation state, that is the reduction of neptunium 6 can go to neptunium 4 and plutonium 6 to plutonium 4. This has been reported, as has been mentioned in the previous Nevada test site report also. Even though we are expecting plutonium 5, that has been reduced to plutonium 4. That is how the plutonium concentration has been much less. Now, why study the actinide substance and migration behavior? This is actually an application part, and whatever we have already studied in the actinide speciation as well as the complexation. In any unfortunate scenario, if there is some leak of the radionuclide to the environment, as I have already mentioned, by accidents or from the vitrified waste blocks which are there under the deep geological repository, from there also if there is some leakage of the radionuclide, then or finally, of course, if from the nuclear weapon testing, there is a lot of actinides are there. So because of that, we try to understand this actinide substance and migration behavior, and this will help us understanding this migration and movement of the radionuclide from one place to the other. And this information is essential due to avoid the radionuclide becoming form a part of our food chain, and also choosing a better buffer backfill materials in case of the deep geological repository, and also the remediation of any radioactive contaminated site. Now, before going to see the interaction between the radionuclide and the clay or oxide surface, let us see some of the properties of oxide clay surface in the aqueous medium. Now, how does the oxide or the clay surface look like in the aqueous solution? The surface oxide and clay has a surface OH group, as I shown here. You have some of these OH groups mentioned here, which is forming a bond with this water molecule here. So many places you have the surface OH group, which is forming a bond with the water molecule here, and that is how it is responsible for forming the complexes with the actinides. And we also have these clay minerals which have the surface hydroxyl groups. I will be showing in the next few slides how these are acting. And the oxides also are present, like we have the silica and alumina, but they also have replaceable hydrogen ions. Some sort of hydroxyl groups are there, and that is how this complexation is taking place. These clay minerals also have a slick-like structure and are composed of mainly the tetrahedrally arranged the silicates and the octahedrally arranged the aluminate groups. And depending upon the arrangement of the silicates and aluminates, the clay can be divided into several groups such as the smectite, kaolinites, etc. It comes in the next few slides. So this is the tetrahedral structure of the silicate structure, and this is the octahedral aluminate structure or aluminum oxide structure. And you have these layers structures where you have these tetrahedral layers and the octahedral layers and another tetrahedral layer. So they form a structure like this. And finally, you have a structure like this, which is given here. So you have the silica to alumina ratio. If it is 2:1, then it can be illite, or a 3-layer 2:1, it can be smectite, as it is given in the next slide. So the structure of the clay minerals are given here. You have this tetrahedral sheet or the octahedral sheet, and you can have another tetrahedral, another octahedral sheet. This is how the stacking can be done. For example, we take this illite. So in this case, we have a 3-layer structure showing having a tetrahedral, octahedral, and a tetrahedral sheet, and this dimension is around 1 nanometer. And this illite actually is a non-expansive type of structure, so where this part is actually having distance is very, very less, where you have the potassium ions embedded between these two types of this seed structures, whatever are there. You have for vermiculite, or which is moderately expansive, and you have this distance is around 1 to 1.5 nanometer. For smectite, it is highly expansive. You have around 1 to 2 nanometer this distance, and water molecules and cations can be there between the two layered structures given here. And similarly for the chloride structure, you don't have, it is again a non-expansive system, and you do not have anything in between these layered structures. Kaolinite, which is at the top, as a non-expansive 1:1 structure. Now the type of charge in the clay. So there are some permanent charges due to the isomorphous substitution in the replacement of one ion for the another one. So this can be like we have one particular set of ions are there, and which is replaced by another set of ions which are having similar size within the crystalline structure. For example, we have this aluminium 3 plus, which is replaced by magnesium 2 plus in the octahedral sheet, or we have this silicon 4 plus by aluminium 3 plus in the tetrahedral sheet. In these cases, you have this replacement of the charge, and that is how you can have also permanent charge is there in the structure of the clay minerals as I have shown. It also can have isomorphous substitution, as it is shown here. The scheme is given here, how this aluminium is substituted by magnesium, and that is how you have a permanent charges present in this structure. So this you have the neutral octahedral sheet, which where you have the aluminium ions. Now there is a net negatively charged octahedral sheet where you have this magnesium is replacing the aluminium. So this is due to the isomorphous substitution. Now the types of charge in the clays, there can be also variable charge. So this is due to the adsorbed ion. Also this is pH dependent charge. You can show these examples here. Adsorbed ion means some ion is adsorbed into this clay mineral, and there will be different charge will be there. Also depending on the pH as shown in this scheme below, you can see that you have this hydrated alumina where at a lower pH value you get this type of structure where these hydrogen ions are there. But if you have a higher pH value, then you find that these hydrogen ions are now removed, so you have the O minus ions are there. So that is how you have the develop the surface charge, that is O minus charges present in the surface, and that can form the complex. Now one important parameter which is considered in case of the clay minerals is the point of zero charge, commonly known as the PZC, will be discussed in this slide. So what is point of zero charge? That is the pH at which the surface charge is zero. It is neither positive charge nor negative charge. So that point is called as the point of zero charge, and it varies from one clay or oxide to the another one. As shown a table here, you can see this point of zero charge. For silica it is 2 to 2.5, kaolinite 3 to 4.6, goethite it is around 7, alpha alumina is 8.3 to 9.4, delta manganese dioxide is 2.8, beta manganese dioxide is 7.2 to 8.7, and albite it is 2, hematite 7.0 to 8.8. So like that, then for different minerals or the clay minerals, we can have the different PZC values. Now for any surface, if the pH of the suspension is the less than that of the PZC, then the surface is net positively charged, and if the pH is greater than the PZC, then naturally the hydrogen ions are removed and the surface is net negatively charged. So some of the important terms which are necessary for this understanding the clay mineral complexation with actinides, they are defined in this transparency, is the specific surface area. This is the unit is meter square per gram. Clay concentration, it can be grams per liter. Surface concentration can be moles per gram. Surface density, moles per meter square. And cation exchange capacity can be milli equivalent, or the CEC is considered as the milli equivalent per gram. Surface charge can be coulombs per meter square, and Faraday constant is 96490 coulombs per mole. So that is how these are defined, and some conversions. The surface concentration, the moles per meter square is the surface concentration moles per gram divided by the specific surface area meter square per gram. Surface concentration in moles per liter can be surface concentration divided by the Clay concentration. Surface charge is defined as the surface concentration multiplied by Faraday constant divided by the specific surface area. Now, how to measure the surface charge of the potential can be done by the potentiometric titration. So you see here how this at a different pH value you can get the surface charge density, and that is how it will be varying initially, and then when it comes down you get this pH value where you have this value is 0, so that is called the charge density is 0, that is called the PZC. So PZC can be measured by potentiometric titration. It can also be done by using an instrument for the where we measure the zeta potential at the different pH values. So this is the photograph of this zeta potentiometer, which is used in the laboratories. So in this case, actually, you automatically you get as a function of pH the zeta potential values, and you can find out for the substances like A, B, and C. You get these are the point of zero charge, where the profile is like this for A, this is for B, and this is for C. So this is how you can get the zeta potential. Thank you.